If you look out across the universe in every direction, something very strange appears. Regions of space that are separated by enormous distances so far apart that light could never have traveled between them look almost exactly the same. They have nearly identical temperatures, nearly identical structures, and nearly identical properties. And that creates a problem because if those regions never interacted, there's no obvious way for them to have coordinated that similarity. In physics, we expect systems to become similar through interaction, through exchange, through time spent influencing one another. But here, we see uniformity without contact, and that raises a deeper question. How did the universe become so smooth when it shouldn't have had the time or the connection to do so? Welcome to the channel. If you're new here, my name is Charles Carroll, and on this channel I explore how structure, information, and persistence shape the universe, from fundamental physics to cosmology and beyond. What we're going to look at today is one of the most important and fascinating puzzles in modern cosmology. Why the universe appears so uniform on large scales, even in regions that should have been completely disconnected. This is often called the horizon problem, but instead of treating it as just a historical issue with a standard answer, we're going to slow it down and really examine what we observe, what the explanation is, and where the limits of that explanation still remain. Because this is one of those places where the universe looks simple on the surface, but that simplicity hides something much deeper. Section 1, what we actually observe. When we talk about the universe being smooth, we're not speaking in vague terms. We're referring to something very specific that we can measure with incredible precision. The key observation comes from the cosmic microwave background, often called the CMB, which is the oldest light we can observe. This light comes from a time when the universe was about 380,000 years old, when it cooled enough for atoms to form and light could finally travel freely. Before that moment, the universe was opaque, filled with a dense plasma that scattered light continuously. But once it cooled, photons were able to move without constant interaction, and that radiation has been traveling ever since. What we see when we map this radiation across the sky is a nearly uniform temperature field, with variations of only about 1 part in 100,000. That level of uniformity is extraordinary, especially when you consider the scale involved. We are not looking at a small region, we are looking in every direction across the entire observable universe and finding that it is almost the same everywhere we look. The differences that do exist are extremely small, and yet those small differences are exactly what allow structure to form later. They are the seeds of galaxies, clusters, and large-scale structure, but they sit on top of an almost perfectly smooth background. To put this into perspective, if the early universe had been even slightly more irregular, the structures we see today might not have formed the way they did, or at all. If it had been perfectly uniform with no fluctuations, nothing would have collapsed into stars or galaxies. So what we observe is a very specific balance, a universe that is smooth enough to be uniform, but not so smooth that structure cannot emerge. That balance is not arbitrary. It reflects a very narrow range of initial conditions that had to be met. From a CWG perspective, this is already telling us something important. What we are seeing is not a random state. It is a highly constrained one. Out of an enormous space of possible configurations, the early universe occupies a very specific region that allows persistence and structure to develop over time. But the deeper issue is not just that it is smooth, it's that it is smooth in regions that should not have had any way to become similar, and that is where the real problem begins. Section 2, the horizon problem. To understand why this smoothness is a problem, We need to think carefully about how systems become similar in physics. In general, systems only reach equilibrium by interacting. Heat flows, particles exchange energy, signals propagate. These processes allow different regions to influence one another and gradually move toward a common state. Without interaction, there is no mechanism for coordination. Regions evolve independently, and differences tend to grow rather than disappear. Now, in cosmology, we can calculate how far light or any causal influence could have traveled since the beginning of the universe. This distance defines what we call the horizon. It represents the maximum region over which different parts of the universe could have exchanged information and come into equilibrium. Anything beyond that horizon would be causally disconnected, meaning there has been no opportunity for those regions to interact or influence each other. Here's where the problem becomes clear. When we look at the cosmic microwave background, we are comparing regions that are far beyond each other's horizons at the time the light was emitted. These regions were never in causal contact. They never exchanged energy. They never had time to equalize their temperatures, and yet when we observe them today, they are almost identical. This is not a small discrepancy. It is a fundamental mismatch between expectation and observation. If physics operates locally and interactions are limited by the speed of light, then disconnected regions should not look the same. We would expect significant variation, not near perfect uniformity. But the universe does not follow that expectation. From a CWG perspective, this highlights a deeper issue. Similarity without interaction suggests that the system was already constrained into a narrow range of states before those regions became separated. In other words, the uniformity we see may not be the result of late-time processes, but something built into the early structure of the universe itself. And that shifts the question from how the universe became smooth to why it began in a state that allowed that smoothness to persist. Section 3, Inflation. The leading explanation for this problem is cosmic inflation. The idea is that very early in the universe's history, extremely early, within a tiny fraction of a second, space itself underwent a rapid expansion. During this period, regions that were initially very close together and therefore able to interact and come into equilibrium were stretched apart to enormous distances. In this picture, the smoothness of the universe is not surprising because those regions were once connected. They had time to exchange energy, equalize their temperatures, and settle into a nearly uniform state. Then inflation took that small, uniform region and expanded it so dramatically that it now spans the observable universe. What we see today is that early uniformity stretched across cosmic scales. This idea does more than just solve the horizon problem. It also provides a mechanism for generating the small fluctuations we observe in the CMB. Tiny quantum variations in the early universe could be amplified during inflation, becoming the seeds of the large-scale structures we see today. So inflation connects two key observations: the overall smoothness and the small deviations that lead to structure. But it's important to stay grounded in what this explanation is doing. Inflation is not directly observed. It is inferred from how well it explains the data. It is a model that fits the evidence, and it does so very successfully, but it also introduces new questions. What caused inflation to begin? What mechanism drove it? Why did it stop? These are not fully settled questions. So inflation provides a powerful framework, but it is not a final answer. It explains how uniformity could arise under certain conditions, but it does not fully explain why those conditions existed in the first place, and that distinction matters. Section 4, Observation versus Reconstruction. At this point, it's important to separate what we directly observe from what we infer. What we actually measure is the cosmic microwave background, a pattern of radiation with extremely small temperature variations. That is the raw signal. Everything else, including inflation, is part of a model that explains how that signal could have formed. This distinction is critical because the signal we receive is not untouched. It has traveled for billions of years through an expanding universe influenced by gravity and other interactions. What reaches us is not the early universe itself, but information that has survived a long chain of transformations. We then take that information and reconstruct a picture of the past using physical models. From a CWG perspective, this is a filtering process. The universe does not present itself directly. It presents what can persist through interaction and transmission. The CMB is not a perfect record, it is a surviving trace, and our models are ways of interpreting that trace, not direct access to the original system. This doesn't make the science uncertain. It makes it precise about what it is doing. We are not observing the early universe directly. We are reconstructing it from the information that remains available to us. And that reconstruction depends on the assumptions built into our models. Section 5. Why this is still not fully solved, extended. Even though inflation explains a great deal, it does not close the problem completely. One of the key issues is that inflation itself requires specific conditions to begin. In other words, we explain the smoothness of the universe by introducing a process that may itself depend on a particular starting state. That raises the question of whether we have solved the problem or simply moved it to an earlier stage. There are also open questions about the underlying physics of inflation. We do not yet have a complete understanding of the mechanism that drives it, and different models of inflation make slightly different predictions. Observations continue to test these models, but the full picture is still evolving. At the same time, alternative ideas exist, though they are less developed or less supported by current data. Some approaches explore different early universe dynamics, while others question whether our assumptions about causality or initial conditions need to be adjusted. None of these have replaced inflation, but they show that the problem is not completely settled. So what we have is a strong working framework that explains what we see, but does not fully explain why the universe began in a state that allowed that framework to work. The smoothness is accounted for, but the deeper origin of that smoothness remains an open question. When you step back and look at the full picture, something important comes into focus. The universe appears smooth not because it had to be, but because only certain conditions could persist and evolve into what we now observe. Whether that constraint came from inflation or something even deeper, what we are seeing today is the result of a selection process. Out of all possible configurations, only a narrow range could expand, stabilize, and carry information forward across cosmic time. The smoothness of the CMB is not just a feature. It is a reflection of what could survive the early universe and remain observable today. Everything else, whatever, did not fit within those constraints, either never formed in a stable way or left no detectable trace. This connects directly to the broader idea that runs through everything we've been exploring. What we observe is not everything that exists. It is everything that can persist under the constraints of the system. The universe does not present all possibilities. It filters them. And what remains is what we are able to measure, reconstruct, and understand. So, the smoothness of the universe is not just a cosmological detail. It is an example of a deeper pattern, one where structure, information, and persistence are all tied together. And when you start to look at the universe through that lens, what once seemed like a simple observation begins to reveal something much more fundamental about how reality is organized. If you've made it this far, you can probably see that the smoothness of the universe is not just a simple observation. It's a window into how the universe formed, evolved, and constrained itself over time. And like many things in physics, the deeper you look, the more you realize that what seems simple often points to something much more complex underneath. Thanks for sticking around if you've made it this far. My name is Charles Carroll, and on this channel I explore persistence, constraints, and the structure of reality. If you found this interesting, consider liking, sharing, and subscribing. It really helps the channel grow and reach more people. And as always, join me next time. Who knows where the science might lead us?